Welcome to MSP lecture series on the chemistry of main group elements. Let me start today the chemistry of group 17 elements. Group 17 elements are called halogens and they are the most electronegative elements in the periodic table having a common oxidation state of -1. So, this oxidation state becomes increasingly reducing on going down the group. So, iodine anion is a moderate reducing agent, while chloride shows few reducing characteristics except with very strong oxidizing agents. For example, if you consider PbI4 is a non-existent compound because of the combination of highly oxidizing and highly reducing species. In contrast, PbCl4 and PbF4 are moderately stable. And besides -1 oxidation state, besides -1 oxidation state, +1, +3, +5 and +7, states occur for chlorine, bromine and iodine, okay. Mainly in oxyanions and also in interhalogen compounds. Compounds in the highest oxidation states generally contain the electronegative elements such as oxygen and fluorine, for example, IF7 or IO4 minus. Fluorine with its small size and high electronegativity coupled with the weakness of the FF bond, it is able to stabilize the very highest oxidation states of elements such as AuF5, NiF4 and PtF6. Okay. That means any metal or any main group element, if it is existing in its highest possible oxidation state, okay, so there is the role of fluorine in it. Okay. So, iodine forms solvated cations. For example, iodine when it is treated with AgNO3 with pyridine, it forms a complex of this type. And let us see the discoverers of halogens. Henry Moissan discovered fluorine in 1886 and William Scheele, responsible for the discovery of many elements in the periodic table, discovered chlorine in 1774. Antony Ballard and Carl Loewy discovered bromine in 1826 and Bernard Cortius discovered iodine in 1811. Very recently in 1940, Dale Carson, Kenneth Mackenzie and Emilio Sager discovered astatine. Let us look into the sources of halogens. Fluorine sources are essentially calcium fluoride, that is also called fluorospar, and calcium fluoride having calcium phosphate, that is fluoroapatite. And essentially elemental fluorine is obtained by electrolysis of Kf dissolved in anhydrous HF. One can see that equation shown here, this equation here. Chlorine essentially obtained from large underground sodium chloride deposits formed by the evaporation of ancient sea, and elemental chlorine by electrolysis of aqueous salt solutions which produce sodium hydroxide as a byproduct. Chlorine compounds have numerous industrial and household applications. Bromine ion occurs in seawater. Of course, the concentration is very low, that is about 30 parts per million. from which bromine is obtained by reaction with chlorine, and sodium iodate NaIO3 from which elemental iodine is obtained by reduction, and iodates are found in some brines from which the element is obtained by oxidation with chlorine. Iodine shows metallic luster and high electrical conductivity under pressure, and astatine is essentially radioactive and all its isotopes are also radioactive, and trace amount of astatine occurs in uranium ore, and of course, uranium ore pitch blende is the source of many radioactive elements that we see in the periodic table. Astatine isotopes are obtained by the irradiation of a bismuth target with alpha particles, from which elemental astatine is obtained in the form of isotopes such as 209, 210 and 211. Let us compare the sources of halogens in both Earth's crust and sea water. In sea water, chlorine abundance is more, whereas in Earth's crust fluorine abundance is more, and most fluorine containing compounds are made using HF. For example, calcium fluoride, when it is treated with the concentrated sulfuric acid, it gives calcium sulfate plus HF. Okay. Difluorine is strongly oxidizing and must be prepared industrially by electrolysis or electrolytic oxidation of F minus ion. The electrolyte is a mixture of anhydrous molten Kf and HF, and the typical electrolysis cell contains a steel or a copper cathode with ungraphitized carbon anode, and mono metal, that is essentially a alloy of copper and nickel, that diaphragm with perforation below the surface of the electrolyte is used, which essentially prevents the combination of H2 and F2 during the electrolytic process. A typical cell is shown here. You can see here steel cathode, and also we have ungraphitized carbon anode here, and of course, inlet is there for HF, and outlets are there for both fluorine as well as hydrogen gas. And commercial chlorine is produced by the electrolysis of aqueous sodium chloride solution in a chloroalkali cell. Let me write the half reactions involved in this reaction. At anode is essentially 2Cl minus giving Cl2 plus 2 electrons. At cathode 2H2O plus 2 electrons gives 2OH minus . Okay. So, here the possibility of oxidation of water is there, that has to be suppressed by using an electrode material that has a high over potential for O2 evolution than for Cl2. So, thus the oxidation of water is prevented. The best anode material for this type of reaction seems to be ruthenium oxide, that is RuO2. This process is the basis of the chloroalkali industry, which produces sodium hydroxide on a very massive scale. And this is the chlorine extraction cell here. You can see here this schematic diagram represents the chloroalkali cell, and of course, all the details are shown here. So, bromine is obtained by the chemical oxidation of bromide ions in seawater. A similar process is also used to recover iodine from certain natural brines that are rich in iodides. The more strongly oxidizing halogen, chlorine, is used as the oxidizing agent in both processes. The resulting bromine and iodine are driven from the solution in a stream of air. Of course, here X equals bromine or iodine. Let us look into the properties of group 17 elements. Difluorine is a pale yellow gas with a characteristic smell similar to that of ozone or chlorine, and it is extremely corrosive, and it is the most reactive element, and difluorine is essentially handled in Teflon or special steel vessels. One can also use glass apparatus provided F2 is free from any dissolved HF gas in it. The synthesis of F2 can be carried out in aqueous medium because F2 decomposes water, liberating ozonized oxygen. F2 is commercially available in cylinders, so there is no need to make it in laboratory. The commercial method involves the treatment of K2, MnF6 with fluorine abstracting reagents such as antimony pentafluoride. Difluorine combines directly with all elements except oxygen, nitrogen and lighter noble gases, and these reactions are very violent in nature. The high reactivity of F2 arises partly from the low bond dissociation energy, because two smaller atoms with high electron density makes this FF bond unstable. As a result, FF bond dissociates readily even on exposure to UV light. When we look into these properties of chlorine, dibromine and diiodine, dichlorine is a pale green yellow gas with a characteristic odor. Inhalation of chlorine causes irritation of the respiratory system, and liquid chlorine burns the skin, and synthesis of chlorine involves the treatment of MnO2 with HCl. Okay. And of course, dibromine is a dark orange volatile liquid, the only liquid nonmetal at 298 Kelvin, and often it is used as a aqueous solution called bromine water. Skin contact with liquid bromine results in burns. One has to be extremely careful while handling liquid bromine. Bromine vapor has an unpleasant smell and causes eye and respiratory irritation. At 298 Kelvin, iodine forms dark purple crystals which sublime readily at 1 bar pressure into a purple vapor. Chemical reactivity decreases steadily from chlorine to iodine, notably in the reactions of halogens with hydrogen, white phosphorus and sulfur and many metals. The observed colors of the halogens arise from an electronic transition from the highest occupied pi star molecular orbital to the lowest unoccupied sigma star molecular orbital. If you recall the MO diagrams that I wrote for first row dimeric species, there, for example, if you consider oxygen, we have 2 unpaired electrons in the pi star antibonding orbital, whereas in case of halogens we have 3 unpaired electrons are there, and here the gap between pi star and sigma star. Pi star is essentially highest occupied molecular orbital and sigma star is essentially lowest unoccupied molecular orbital, between which the gap is small and the electron transition can readily occur. As a result, some of these halogens are colored in nature. The HOMO-LOMO energy gap decreases from fluorine to iodine. That means transition is very facile when you go from fluorine to iodine. Okay. Solutions of I2 in donor solvents such as pyridine, ether or ketones are brown or yellow because of formation of the adducts that I showed in a couple of minutes back. Even benzene acts as a donor, forming charge transfer complexes with iodine as well as bromine. In dichloromethane solution, triphenyl phosphine dibromide ionizes to give salt of this type. For example, if you consider PH3P Br2, this ionizes to give PH3P Br plus and minus. Similarly, iodine also forms iodine minus. Of course, in presence of excess of iodine, it can also lead to the formation of I3 minus, or it can be even I5 minus. The nature of products from reaction of PR3 and I2 are dependent on the solvent and the R group on phosphine. Solid state structure determination exemplify products of this type. For example, I will show you in the next slide. You can see this has been isolated where between two phosphines we have 5 iodine atoms. So, essentially this is I3 plus and again I3 minus. Okay. The composition or structural formula can be written in this fashion. So, let us look into the Clathrates. Dichlorine, dibromine and diiodine are sparingly soluble in water. By freezing aqueous solutions of chlorine and bromine, solid hydrates of approximate composition X2,8H2O. May be obtained. These crystalline solids are essentially known as Clathrates. Okay. So, these crystalline solids consist of hydrogen bonded structures with X2 molecules occupying cavities in the lattice. A Clathrate is essentially a host guest compound, a molecular assembly in which the guest molecules occupy the cavities in the lattice of host species. Okay. So, let us look into the hydrates of group 17 elements. All the hydrogen halides, that is HX, are gases at 298 Kelvin with sharp acid smells. Direct combination of hydrogen with halogens to form HX can be used synthetically only in case of chloride and bromide. So, hydrogen fluoride is prepared by treating suitable fluorides with concentrated sulfuric acid. Analogous reactions are also a convenient means of making HCl. Analogous reactions with bromides and iodides result in partial oxidation of HBr to HI, HBr Hi2, Br2 or I2 respectively. HBr and HI are prepared from corresponding phosphorus trihalides. Let me give the synthetic procedure for these halides. For example, CaF2, when it is treated with concentrated sulfuric acid, gives 2HF. Of course, CaHSO4 twice. Similarly, 2HBr plus H2SO4 gives Br2 plus 2H2O plus SO2, and PX3 plus 3H2O gives 3HX plus H3PO3, where X equals bromide or iodide. Okay. Hydrogen halides are known and stability of these hydrogen halides decreases down the group owing to the increasing mismatch in atomic sizes. For example, if you consider HF, we have 1s hydrogen and 2p fluorine, when we go further it becomes 3p, 4p and 5p, and steadily the size of these orbitals are increasing. Due to the mismatch of the overlapping orbitals, the stability decreases down the group and it is expected, and Hi is rather unstable. For example, delta HF is positive, is plus 26.5 kilojoules per mole, okay, and Hi exists in equilibrium with H2 and I2. So, always okay. So, the melting and boiling point increase down the group with the exception of HF, which has a very high boiling point due to extensive hydrogen bonding. In fact, even in gaseous phase HF retains this hydrogen bonding. So, this HF unit is always linear about the hydrogen and also occurs in the so called hydrogen fluoride salts such as KHF2. Is linear, and also it is observed in salts such as KHF2. Okay. The hydrogen halides dissolve in water to give highly acidic solutions. And HCl, HBr, Hi all are very strong acids and are essentially fully dissociated in dilute solution. However, HF is a much weaker acid. That is again due to the extensive hydrogen bonding. One can see in this slide the structure of HF in the solid state, and this kind of structure is also retained even in the gaseous phase. Okay. Let us look into metal halides. All the halides of the alkali metals have sodium chloride or cesium chloride structures, and cesium fluoride is the best choice of alkali metal fluoride to effect the halogen exchange reaction. That means, it is a good fluorinating agent. For example, if we take CCl and if we treat this one with cesium fluoride, okay. Cesium fluoride is the best choice of alkali metal fluoride to effect the halogen exchange reaction, and that means cesium fluoride is a very good fluorinating agent. If you take this CCl bonded compound and treat with cesium fluoride, fluorine exchange takes place to form fluorinated compound along with cesium chloride. A few other monohalides possess the sodium chloride or cesium chloride structure, for example, silver fluoride as well as silver chloride. These compounds exhibit significant covalent character. That is true in case of cuprous chloride, cuprous bromide, cuprous iodide and also silver iodide, which possess the Wood-Reich structure. So, let us look into halogen oxides. All halogens form oxides. Those of iodine are the most stable, while those of bromine tend to be the least stable. And of course, all oxides of halides are oxidizing agents, and dihalogen monoxides of this type are known. For example, E2O, is OF2 plus 2F minus plus H2O. OF2 is the most stable and is a very powerful oxidizing agent. It can even oxidize water to oxygen, and OF2 explodes when mixed with halogens, but a spark is required to ignite mixtures of OF2 and hydrogen or carbon monoxide. For example, if you take OF2 and treat with water, water is oxidized to oxygen through the liberation of HF. Similarly, if you consider Cl2 plus 2HGO, this is the method for the preparation of Cl2O through the formation of HgCl2 HgO. So, iodine is the only halogen to form an oxide which is thermodynamically stable with respect to decomposition into its elements. Chlorine and bromine oxides are hazardous materials with a tendency to explode. Chlorine oxides, although not difficult to prepare, all are liable to decompose explosively. Far less is known about the oxides of bromine, which are very unstable than those of chlorine as well as iodine, although one can prepare Br2O3 and Br2O5 using convenient synthetic routes. Okay. For example, if you take Br2 and treat with ozone at 195 Kelvin, okay, it can form Br2O3, which on further treatment with ozone at the same temperature, it gives Br2O5, and formation of this one can be concluded visually by looking into the color. Initially it is brown and it changes to orange, and eventually when Br2O5 is formed, it is colorless. Bromine 5 centers are trigonal pyramidal, and in Br2O5 and BrO2 groups are eclipsed. So, dichlorine monoxide Cl2O is obtained as a yellow brown gas by action of Cl2 on mercuric oxide or moist sodium carbonate. So, other reaction I wrote, let me write another method here. So, this Cl2O liquefies at minus 277 Kelvin and explodes violently on warming. It hydrolyzes to hypochlorous acid and it is formed the anhydride of this acid. For example, if you take Cl2O plus water, it gives 2HOCl. Okay. Chlorine dioxide ClO2 is a yellow gas and is produced in the highly dangerous reaction between potassium chlorate KClO3 and concentrated sulfuric acid. One has to be extremely careful in performing this reaction if one has to do it. Or one can also start from NaClO3 in the presence of SO2 and sulfuric acid. Okay. And one can also write in the following structures. These are the possible resonance structures for ClO2. ClO2 is a yellow gas, explosive in high concentration and prepared by the reduction of KClO3 in acidic solution, and this is also paramagnetic molecule. You saw having one unpaired electron. Because of delocalization of the unpaired electrons over the entire molecule, it shows little tendency to undergo dimerization. However, in the solid state, it forms loose dimers with a ClO distance of about 270 picometer. Of course, the normal ClO bond distance is 147 picometer, and ClO2 is commercially an important bleaching and sterilizing agent. It dissolves unchanged in water, but is slowly hydrolyzed to HCl and HClO3 involving ClO radical. Ozone reacts with ClO2 at 273 Kelvin to form Cl2O6, a dark red liquid which is also made by following reaction that I am going to write now. Of course, if you are curious to know the structure of Cl2O6, this is how it looks like. We have a oxygen bridge here. So, let me stop here, and in my next class I will continue from here. I need another lecture to complete group 17 elements, then I will move on to group 18 chemistry. Until then, have a pleasant reading of main group chemistry. Thank you very much.